Last week we left off talking about how the Stefan-Boltzmann law was used to predict the temperature of an object. Using that law, we observed that the Earth's temperature is predicted to be a balmy negative 18 degrees Celsius, a place in which we couldn't survive on Earth. Instead, we know the Earth has an average temperature of about 14 or 15 degrees Celsius, and that warming is caused by the greenhouse effect. So let's talk a little bit more about what is it about greenhouse gases that causes this effect. We also chatted briefly last week about the composition of our atmosphere. We know the majority of our atmosphere is made up of nitrogen, oxygen, and argon. Although these gases make up 99+% of our atmosphere, they are not the ones that are controlling the greenhouse effect. When we consider all atoms and molecules, each of them have a unique way of interacting with electromagnetic radiation. Each atom or molecule absorbs and emits radiation at characteristic wavelengths. You can think about these as fingerprints. Each person has its own unique set of fingerprints, and the same is true for which wavelengths of light may be emitted or absorbed by a given element or molecule. So nitrogen, oxygen, and argon are essentially transparent to visible wavelengths of light. What that means is when the sun gives off light, and we know it gives off light in UV, visible, and infrared portions of the electromagnetic spectrum, nitrogen, oxygen, and argon are not capable of absorbing the visible light that comes from sunlight, making these molecules or atoms basically transparent to visible sunlight. On the other hand, we talked about how there are other trace components of our atmosphere, such as carbon dioxide, methane, water vapor, and some other gases. Most of these gases also let in visible wavelengths of light from the sun. However, their fingerprints enable them to absorb infrared light that's being emitted from the Earth via black body radiation. So we can actually look at a spectrum, and this takes a little bit of time to dissect what this looks like, so we're going to walk through it slowly. If you look at this particular figure, you'll see that you have UV light, visible light, and then as it extends down to the right, this is infrared light. The red line is characteristic of all of the wavelengths of light that are emitted from the sun. The shaded red area underneath the big red line indicates which wavelengths of light actually from the sun make their way down to the Earth's surface. What you'll notice is that almost all of the light in the visible region is shaded in red. That shows that almost all of the visible light from the sun makes it all the way down to the Earth's surface. However, you'll notice that much of the area in the UV region is white. Very little of it is red. The reason for that is our atmosphere is able to absorb these higher energy wavelengths of light in the UV region, which is good for us because then we aren't exposed to this higher energy form of light. And then we'll also notice as we go down into the infrared region of the electromagnetic spectrum, there are small portions of the infrared light transmitted by the sun that don't make their way down to the surface of the Earth. Conversely, we can look at another spectrum. This time the spectrum is showing the infrared radiation coming from the Earth's surface. So you'll notice they give 3 different curves representing different black body radiation temperatures. All of them are temperatures in the ballpark of what the Earth would be, or a little bit colder. But what you'll notice about them is that they're all giving off characteristic wavelengths of light in the infrared region. Recall, the Earth is much cooler than the sun, and as a result, the black body radiation it gives out is going to be infrared light or heat. That's what you're used to thinking of it as. And so the Earth's IR radiation that comes off is a range of infrared light. And then what you'll notice is under that range of light, there's a shaded blue region. The shaded blue region is the portion of the heat radiating from the Earth that actually makes it through the atmosphere. The rest that is white indicates areas where that energy is absorbed by the Earth's atmosphere. So what we have here is greenhouse gases present in our atmosphere that are good at absorbing various wavelengths of infrared light and trapping that heat. So we can sum all of this up by saying that the greenhouse effect is the effect that enables the recycling of thermal energy that's radiating off of this Earth's surface. And rather than letting that thermal energy simply escape back into the surroundings outside the atmosphere, the greenhouse gases in the atmosphere are excited by various wavelengths of infrared light and trap that heat. This enables us to have an Earth that is over 30 degrees Celsius warmer than it would be predicted to be. So we want to think a little bit more about how this works in terms of which greenhouse gases are doing what. So we're going to break down the electromagnetic spectrums from the sun and the Earth into a little bit more detail now. All right, so there's a lot going on this graph. I'm going to walk you through it. What you'll notice again is the UV, visible, and infrared light that is the black body radiation coming off of the sun, and then the infrared wavelengths of light that are emitted from the Earth. When you look at these spectrum, we can actually break it down more closely into what type of gas is absorbing various wavelengths of light. So we're going to start with water. Water is the most important greenhouse gas. You'll notice if you look at the spectrum of water, what's happening here is anytime you see gray, those are regions that water is absorbing electromagnetic radiation. So if you remember the areas from the sun that have infrared light that doesn't make it down to the Earth's surface, that is primarily due to water absorbing some of those wavelengths of light. You'll see how they match up over here, where the gray regions match up with the white regions in the sun's spectrum. Also, when you look at water, you'll notice that it heavily absorbs infrared light in the regions where you have radiation from the Earth. So you see a large portion of infrared light absorbed here and a ton of infrared light absorbed at the right end of this spectrum. So water is by far the most important greenhouse gas because it's capable of absorbing lots of different wavelengths of infrared light. The second most important greenhouse gas is carbon dioxide. That's the one you're probably used to thinking about more often with respect to climate change. You'll notice that carbon dioxide has a handful of wavelengths where it's good at absorbing infrared light. You'll notice that they partner nicely with areas where water doesn't absorb as well. After carbon dioxide, there's other greenhouse gases that we will talk about throughout the course of the semester. Things like methane and nitrous oxide also are important players that absorb light in some key regions of the infrared spectrum. When we talk about all of this, you'll notice that I said water is the most important greenhouse gas, but it almost never gets coverage in the media. The reason for that is water is typically always there in some amount. The concentration of it is typically stable over time, and so human activities that result in global warming are typically not heavily changing the concentration of water in the atmosphere, and as a result, while it's the most important greenhouse gas, it's not the one we talk about when we talk about current climate change. The reason for that is when we think about various greenhouse gases, how much they contribute to absorbing various wavelengths of infrared light depend on the amount of gas present, how effective that gas is at trapping heat, and how long that gas lives in the atmosphere before it goes away. So this table I'm showing you here talks about the average lifetimes and warming potentials of various greenhouse gases. You'll notice that the first greenhouse gas listed is carbon dioxide. Again, water is not typically considered because it doesn't change as much over time, so everything is normalized to carbon dioxide in this table. So carbon dioxide has an average lifetime in the atmosphere of somewhere on the order of 50 to 200 years. So that means that if you burned some gas to drive your car here today, that the CO2 that is emitted from the burning of that gas will stay in the atmosphere for up to 200 years. Another important greenhouse gas, methane, is a very important greenhouse gas, but it doesn't stay in the atmosphere as long as carbon dioxide does. Its average lifetime is about 12 years. However, when we talk about greenhouse gases, methane is actually very important because it is much more potent molecule per molecule compared to carbon dioxide. It has a potential to warm the atmosphere about 20 times more than carbon dioxide does. We can go on down the line and look at some other greenhouse gases. Nitrous oxide has a residence time of 120 years and has an even greater global warming potential compared to carbon dioxide. However, nitrous oxide is much less abundant in the atmosphere, so even though carbon dioxide doesn't have the same amount of warming potential, its larger concentration is the thing that we consider most when we talk about climate change. These next three molecules are different types of refrigerants, and what's most important about them is that they have very strong warming potentials compared to carbon dioxide. So even if their concentrations in the atmosphere are low, small amounts of these various molecules can do a lot of damage. So again, carbon dioxide is the second most important, primarily due to how long it lives in the atmosphere and its abundance, but other greenhouse gases are important particularly because of how potent they might be as greenhouse gases. When we put all of this together, the bottom line is that the greenhouse effect has a major role in how warm our climate is. If we didn't have water or CO2 or these other greenhouse gases in the atmosphere, our Earth would be so cold that life would not exist. So it's good that we have some amount of greenhouse gases warming our atmosphere. However, now that we've solved that mystery, it leaves us with more questions. The first question is, what causes our climate to change? And then, is the current change we're observing natural? For us to answer either of those questions, first, we have to understand how greenhouse gases naturally cycle in our atmosphere. We need to know those cyclings to understand their relative concentrations and what might change how much of those greenhouse gases is in the atmosphere. Once we're able to answer that question, then we can start to investigate how human activities modify these fluxes.